So last time, in the section on the ratio and root tests, we talked about the ratio test specifically. And I said that these are the last tests that we'll encounter in our exploration of series. But then the last part of Chapter 9 has to do exclusively with applying these tests in the context of power series, which are essentially infinite polynomials, if you will, okay? So that's exciting. And the whole point is we can oftentimes turn a function, no matter how complicated, into a infinite polynomial, i.e. a power series. But then we need to know stuff about it, like what values of x are we allowed to plug in at all and still get a converging series, okay? So that's why we're doing all this stuff. We have one more test to do, and that's the root test. But before we do that, I wanted to remind you of what the ratio test said, okay? So somebody hands me a series, and it could have negative terms in it, right? Now, we have a few tests that actually are useful in the context of having negative terms. One of them is called the nth term test. The nth term test works no matter what. But it can only tell you if a series happens to diverge, right? The next test that we encountered that can handle negative terms was technically the limit comparison test, right? I told you that. Limit comparison test essentially allows you to be able to replace the terms in a series with something that behaves similarly, and then you can make conclusions from there. Then there was the alternating series test, right? So that also gave you a way to discern what's happening with series that happen to have negative terms. But the alternating series test required that they alternate back and forth between positive and negative terms. The ratio and the root test, though, actually deal with series where you may or may not have negative terms, right? But what it tells you is when the series happens to converge absolutely. Okay. But there is one situation where it doesn't tell you anything, and that's in the situation where the limit of the ratio of consecutive terms goes to 1. The reason we don't know anything is we have examples of series where that happens and the series diverges. But we have other examples where that limit is 1 and the series converges. So that tells you that there's kind of like, there's not the ability to make any kind of conclusion in that case. And what did I say is going on when the limit of the ratio of consecutive terms in absolute value is less than 1? What did I say that series is basically behaving like? The geometric with common ratio less than 1. And in the second case, if the limit of the ratio of consecutive terms is bigger than 1 or infinity, then you end up with a series that is behaving like a geometric with common ratio greater than 1, which we know diverges. Yes. And the third case is inconclusive, namely where the limit of that ratio is 1 exactly. Okay, let's talk about the root test. Okay, the root test. Root test. So when we talk about the root test, we are specifically interested in nth powers here. If the terms are like raised to the power n, then it turns out the root test is going to be fairly nice. Okay, and the rationale here is exactly the same as it was for the ratio test. I mean, think about it. If my terms were like equal to 1/2 to the power n, if my terms were all 1/2 to the power n, what would happen if I took the nth root of 1/2 to the power n? What would I get? What would I get if I took the nth root of 1/2 to the power n? You would just get 1/2. It's that simple. Yeah? If my terms were 1/2 to the power n, and I took the nth root, I would get 1/2. And then when I took the limit as n goes to infinity, that doesn't go anywhere. That just stays right at 1/2. You know what I'm saying? So once again, number one is basically detecting whether the series happens to be behaving like a geometric with common ratio less than 1. In the case of an equal to 1/2 to the n, the common ratio would be 1/2, and that would be what your limit is. Does that make sense? Okay. Okay. And similarly, the second case, series will diverge if the nth root of the terms is bigger than 1. What that basically says is that this series is behaving like a geometric with common ratio bigger than 1. Do you know what I mean? So for instance, if the terms were like 3/2 to the n, okay, if the terms were like 3/2 to the n, and I took the nth root of that, what would I get? 3/2, which is bigger than 1. But what do you know about the series where the terms are 3/2 to the n? Is that a converging or a diverging series? That diverges, yes, that series would diverge. We would have a common ratio bigger than 1 in that case. And once again, the root test is inconclusive if the limit of nth roots of an, by the way, an is always an absolute value, is equal to 1. And again, the convergence here is absolute because we're taking the absolute value of the terms. Okay? Hang on a second here. I'm having an issue with my iPad. So hang on a sec. All right. Here we go. So once again, if the terms were like, here, I'm going to just write these in here just so you can see them. If the terms were something like an equal to 1/2 to the n, then if I take the nth root of these things, right, and of course I take the absolute value of this, that's not really going to make a difference here, and I take the nth root of this, then the nth root of the nth power, that just ends up being 1/2, which of course if I let n go to infinity, that just stays right at 1/2, which is less than 1. And of course I know flat out that the series 1/2 to the n is a converging series, yes? So in some sense, this test is also detecting whether we are dealing with basically something that's like a geometric, yeah? Okay, and it makes conclusions based on that. Okay, couple of things I want to draw your attention to that I did last time. Do you guys remember what is the limit as n goes to infinity of n to the 1 over n? By the way, the nth root is the same thing as raising something to the 1 over n power, correct? So what is the limit as n goes to infinity of n to the 1 over n? 1. What about the limit as n goes to infinity of n to the 78 over n? That's also 1 because that's going to be like n to the 1 over n raised to the 78th power. 1 times 1 times 1 times 1, 78 times is still 1. What about this? What about the limit as n goes to infinity of bn raised to the a over n, where a and b happen to be constants? What do you guys think? Still 1. Okay? Those are going to be important limits that will actually come to our aid when we start doing examples with the applications of the nth root test. Okay? All right, are you guys ready to do some examples? Let's do it. Okay, so again, if the nth root of the absolute value of the terms goes to something less than 1, you have an absolutely converging series. If the nth root of the absolute value of terms goes to something greater than 1, you have a diverging series. And again, this is kind of going back to the geometric series. What's going on in the first case is you basically have a common ratio less than 1, and in the second case, you have a common ratio greater than 1. And the root test is inconclusive if that limit happens to be 1. Which test did I say is more powerful overall? The root test. Root test actually will always tell you something whenever the ratio test does, and more, right? The root test actually will apply and tell you something in situations that the ratio test fails to tell you anything. Okay? But that also relies on you knowing things like Stirling's approximation, which is a little bit gnarly to keep in your mind, right? talked about that before. All right, but let's do some examples. Okay, first example, we did this one last time, but let's look at this. What about, I'm going to let you kind of work on this for a couple minutes. Okay, sum in going from 1 to infinity, minus 1 to the n minus 1 times 3/2 to the n over n squared. Okay, so think about that with people around you and apply the root test and tell me what the conclusion is. And remember, you take the absolute value of the terms, which what is that going to do immediately? Get rid of the minus 1 to the n minus 1. Yes, that stuff is just gone. Okay, and all that's going to be left is that other junk. So take the nth root of the terms, and we'll reconvene in a couple minutes, and you can tell me what happened. All right, help me out here. What do you got? Yeah?
So take the limit as it goes to 3/2 the n over n squared, all to the 1 over n power.
Uh-huh.
Having n squared in the denominator leaves as negative 2 n raised to the negative.
So hang on, Daniel. So you're saying that this part right here is what you're left with when you take the absolute value of an. So if an is everything, that part that I boxed is absolute value of an. And you're saying to raise that thing to the 1 over n power, yeah? Which is, if I raise that to the 1 over n power, what does that do to 3/2 to the n? Yeah, you just end up with 3/2. And what do you get on the bottom, Daniel? Into the, yeah. And then you're saying take the limit as n goes to infinity. And what do you get? Right, because into the 2 over n, as we just talked about, that goes to 1, correct? So overall, this goes to 3/2, which is greater than 1. So what do you conclude, Daniel? Right. So the series diverges. So the series diverges by the root test. We did the same, we actually did the same problem last time, yeah? But when we used the ratio test. And by the way, that makes sense. Think about it. The terms, hello, the terms aren't even going to 0. Correct? When we talked about this last time, the numerator is 3/2 to the n. That goes to infinity, correct? N squared goes to infinity. But which one goes to infinity faster, 3/2 to the n or n squared? 3/2 to the n, the exponential whips the polynomial. Therefore, the terms aren't even going to 0. Therefore, is there any chance to get convergence here? No. By which test, honestly? Which test tells us that the terms, the nth term test, okay, the terms do not go to 0, therefore you do not have a chance to converge. Yeah, this thing diverges. Yes?
Would it be possible to pull that like 3/2 out in front of an e and then raise e to the limit and then like?
Yeah, right. So if you forgot about into the 2, okay, so the question here for those online, what if you forgot that into the 2 over n went to 1? Which, by the way, I highly recommend that you not forget that. But in case you did, yes, you could do the e to the logarithm thing. And because you would have something of the form infinity to the 0, which is indeterminate. If you do the e to the logarithm thing, the power would come down, and you can apply L'Hopital's rule to what's left, and you would get that limit was 1. Yeah. No, right. So that's actually how we did into the 1 over n, and it turns out that the same method works no matter what. Yeah, that's right. Okay, ready for another one here? Let's do another one. How about this? So How about this? How about the sum? Oops. Sum n going from 1 to infinity of n over 2n plus 1 to the n. Okay, so think about that with someone nearby, and we will talk about it in a few. All right, so this one should have collapsed rather quickly. Okay, so in this case, what is our an? So this is an. So if I take the absolute value of an and I raise it to the 1 over n, okay. So what happens to the 1 over n and the power n? They cancel, and you just are left with what's inside the parentheses itself. So you just get n over 2n plus 1, which, what does that go to? Right, this goes to 1/2, which is less than 1. So what's the conclusion? So the series converges. Actually, I mean, this is sort of stupid, but you could say that it actually converges how? I'm going to even put that parenthetically here. Why is that not really all that exciting in this case? Because there aren't any negative terms, for crying out loud, right? All the terms were positive to begin with. So the series converges absolutely by the root test. I almost said ratio, but then I changed. It is exciting. Absolute convergence is exciting, though, for primarily one reason. Namely, you know that even if I took these terms and like moved them around, and like jumbled them up, I wouldn't get a different sum. Does that make sense? So that is possible to happen if I have a series that converges. What was the other type of convergence? Conditional convergence, where like it doesn't converge in absolute value, but it does without the absolute values. Those conditionally convergent series are weird. Jumbling up the terms potentially gives different values for the sum. Yes?
I'm curious, could you just ignore that plus 1 and then take out the n's and just have it be 1/2 to the n?
Well, yeah, but that's essentially what happens when you take the limit. Yes, you could. So Michael is saying, hey, can't we just ignore the plus 1? The answer is yes, but what are you technically using when you do that replacement? You're doing another test, limit comparison.
Yeah.
So you could do this problem using limit comparison with the geometric series 1/2 to the n. Does that make sense? If you compared the terms, so let me just kind of make this clear. Look, if I take 1/2 to the n and I put it over n over 2n plus 1 to the n, look what happens. I get, what do I get? Like things are going to flip, right? And I'm going to get 2n plus 1 all over what? 2n raised to the n. Yes? Does that make sense? Which, by the way, this is a nice segue. I didn't even plan this, but watch what happens here. This is like 2n over 2n plus 1 over 2n, right? Which, do you guys believe me that that's like 1 plus 1/2 over n raised to the n? And I am telling you, if I take the limit of this as n goes to infinity, you get e raised to what power? E raised to the 1/2. Right? And the reason it's e raised to the 1/2 is because there's a 1/2 sitting right here. Okay? And that's something that you're going to have to actually show why it happens to be true here in just a minute. Okay? So that since that thing goes to the constant square root of e, though, the limit comparison test says that the series 1/2 to the n behaves exactly like the series that we have here. Yes? Right, so that's kind of what Michael's driving at here. But that is a different test. What test is that again? That's limit comparison. So saying that this test or this series behaves like series 1/2 to the n, because when I take the ratio of the terms, that limit goes to a positive constant. Yeah. Any questions on that? Yeah, Daniel. Yes. Yes, we'll do that at the beginning of tomorrow. So let me just show you what the plan is for tomorrow. Okay, so can I delete this? Okay. So there's a few slides at the end here, guidelines for a series for convergence or divergence, right? We're going to go through, and I mean, even though I've kind of talked about this, like I go through, you just kind of systematically think through which ones you need to use. But then there's like some tables that we'll kind of talk through at the beginning of next time also. These are all the different tests that we have right here. Okay, so we sort of organize our thinking in that way. And then we will then springboard into the realm of Taylor polynomials tomorrow, which is the start of our power series discussion. So that's where we're headed over the next few days. And then we'll be done with chapter 9. Okay, which is all of series. This is what I said was kind of the penultimate fearful time in calculus. So hopefully if you've been feeling pretty good so far and you're like, okay, I'm feeling pretty good about this. We're almost through chapter 9. And by the way, I think the next exam is sometime like maybe the first or second day in October or something like that. So you can check that on the schedule. We're right on schedule though. Okay? All right. But that's for tomorrow. And right now, we are going to have a quiz.